Welcome to a new problem. This time we have an elevator. There's a cable that supports the elevator, and it just so happens that the whole elevator, we're assuming usually it has people inside, but you can also assume that we don't have anyone inside the elevator. So the mass is supposed to not exceed. So, m has to be less than or equal to 3,100 kilograms. That's the mass of the elevator. Another thing that happens is this cable right here that supports the elevator has a diameter of the actual diameter of the cable happens to be um, the part that we're looking for. So we want to find what this diameter is. The other thing that happens is the safety factor, N. Remember, N is the safety factor. Each cable has to be safe, and so N is equivalent to 8.0, and we're going to use that in the problem. G, which is the acceleration due to gravity, is 9.8 meters per second squared, or 81 meters per second squared. The elevator itself has an acceleration, or the maximum acceleration would be equivalent to 1.8 meters per second squared. So this is the information we're given, and we want to find this diameter. That's our goal. That's the goal of the elevator. First of all, the force involved. So there's a force that's holding on to the elevator, and that force is coming off of the cable. So we want to compute that force, which is equivalent to the mass, the total mass of the cable, this one, times the combined acceleration, the cable and or the way you can see it is that there are two components to this force. The one that provides the acceleration, and then the one that provides the acceleration due to gravity. This is the movement of the cable beyond the gravity. And so we have the mass itself, 3,100 kilograms, times 1.8 meters per second squared. And then we add that to the force responsible for the acceleration due to gravity. That's the second component. The total becomes around about 35,991 newtons. It's a huge force. But our goal, again, like we said, is to get the diameter, this one right here. We know that the stress on the cable is, if you can recall, stress is usually force per unit area, but on this one it has a different dimension. So it's 4F all over pi d squared, where the symbol for stress is sigma. So on our next page, we say that sigma has to be equivalent to 4 times the force we're given, 4 times the force we're given over pi d squared. And of course, you're saying, how is this going to help us? Well, it's going to help us because the safety factor N is equivalent to the ultimate strength of the cable. This is the ultimate strength. All over the stress of the cable. And because this is the stress, we can define the safety factor as the ultimate strength of 4F times pi d squared over pi d squared. Or we can say this becomes equivalent to the ultimate strength. The d squared comes up. And then we also have, we could simplify this. We could simplify this by saying the ultimate strength divided by 4F all over pi d squared. And that makes us simplify our safety factor by flipping the stress fraction. So 4F, so this one was flipped, this fraction was flipped. And so we have a new definition of safety factor, mu ultimate strength times pi d squared all over 4F. Again, we can solve for d squared by multiplying both sides by the reciprocal 4F of sigma squared pi times 4F over sigma squared pi. And so d squared into the safety factor times 4F all over the ultimate strength times pi. And then in the next page, we can always aggregate these variables in the problem. And so we, just to make sure things are correct, we have d squared being equivalent to, I just want to check that, n 4F all over the ultimate strength times pi, the ultimate strength times pi. And that can help us. It's always a good habit to keep the variables up until the end before you plug in the actual numbers. That's giving us the diameter. The ultimate, the safety factor was 8 times 4. And then the force itself was given as 35,991 newtons. We want to divide all of that by the ultimate strength, which is in pascals, so 500 times 10 to the 6 Newton per meter squared. That. And then we also want to multiply that by pi. You could see that these newtons are going to cancel out. And because this is a square, there's a radical. That radical, this will come up in the solutions. The radical, we get rid of one of the squares, and then we're left with m. So our final answer, when we simplify that problem, becomes 0.027 meters. So that's the solution to the problem. Just making sure that we're comfortable with the ultimate strength, not the ultimate strength, but the diameter. First of all, we have to find the force involved, and then we have to use the stress to look at the relationship between the force and the diameter. The stress is sigma. And then on top of that, we have to go back. One of the things I think we forgot is, one of the things we're using the stress to simplify the problem. So we get rid of the stress and replace it with these variables that involve the ultimate strength together with the diameter and the force involved. And then based on division algebraic manipulation, we're going to flip this fraction. And when you flip it, knowing that the safety factor is 8, and the ultimate strength, or the ultimate strength, is 500 times 10 to the 6 pascals, we can always go ahead and plug those numbers in with the radical and get your final solution. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.